In this video, we're going to talk about proving that triangles are similar to each other. So in this first question over here, we are told that angle RPT is congruent to angle RSQ. And it's asking why the big triangle PRT and the small triangle SRQ are going to be similar to each other. So it already gave us one pair of congruent angles from the givens. And then if you notice, the small triangle is SQR and the big triangle is PTR. They both have R in it. And that's because R is shared between the small and the big triangle. So that's a second pair of congruent angles. So AA justifies why the triangles are similar. And most of the time when we're proving triangles similar and we don't have numbers, AA is going to be the way to go. And that's going to lead us into the proofs that we're going to do in just a minute. ASA is not even a similarity shortcut. It's a congruent shortcut, but not a similarity shortcut. SAS and SSS require numbers because the S's stand for proportional sides, so those require numbers. Here, we have PS is parallel to QR, and we need to figure out how we can prove that triangle PST is similar to triangle RQT. Well, we don't have any numbers, so right away, we know it's going to be AA, and it's not ASA because ASA is not used to prove triangles similar, but just to justify it, we have parallel lines cut by a transversal, so we do have a letter Z. So we do have congruent alternate interior angles. We also have a letter X from intersecting lines, so we have congruent vertical angles. So those are our two pairs of A's. If we take a look over here at this question, we're told that D and E are midpoints of the sides that they're on, AB and AC, and DE is drawn, so DE is a midsegment. And it's asking which methods could be used to prove that the triangles are similar. So if DE is a midsegment of the triangle, it's parallel to the third side. So that means corresponding angles are congruent. And there's also the shared angle A. So AA similarity does work to prove the triangle similar. We do have congruent angles. If D and E are midpoints of the sides that they're on, that means D splits AB equally and E splits AC equally. So we can see that the side of the big triangle would be double the side of the small triangle. For example, if this is 2 and this is 2, this has to be 4. So AB, the side from the big triangle, would be double AD, which is the side from the small triangle. So there is a scale factor of 2. And that scale factor holds for all of the sides because the triangles are similar. So it's going to be the same scale factor for all the pairs of corresponding sides. So from AE to AC, it's going to be a scale factor of 2. And from DE to BC, it's going to be a scale factor of 2. So SSS similarity holds. All the sides are proportional by the same scale factor. And SAS also holds because if these two sides are proportional and we have the shared congruent angle in between, we do have side angle side. So all of these could be used to prove the triangle similar in the special case where we have midsegments. Over here, I already see we have numbers, so I think one of the other ones might apply other than AA, but we can check it out and see. So we have angle GRS congruent to angle ART, and we have some measurements of the sides. The measurements of the sides are surrounding the congruent angles, so that's looking like SAS to me, but let's verify. In order for it to be SAS, we do need to just double check that the corresponding sides are proportional to each other. So let's check it out. I'm going to do 45 over 18. And I'm going to see if that is proportional to 36 over 15. So let me get my calculator out. And I'm going to do 45 times 15. And that's 675. And then I'm going to do 18 times 36. Oh, and that's 648. That doesn't check out. We don't have another pair of angles, so it can't be AA. We don't have the other pair of sides, so it can't be SSS. So it has to be that the triangles are not similar to each other. Look at that. So it's always good that we check if the sides are proportional. As we were speaking a little bit about before in the video, when proving triangles similar in a 2-column proof, we are generally going to prove the triangle similar using AA because we don't have numbers. And for SIS and SSS, most of the time we need numbers because we do need proportional sides. Here, we're told that angle ACB is congruent to angle AED, and we need to prove that the triangles are similar. This proof is a quick one because if you take a look at the small and the big triangles, the small triangles inside the big triangles, so they do have a shared angle, and that shared angle is angle A. So if I was writing this up in a 2-column statement, reason, chart proof, after I write the givens and one of my angles, the brown angles, comes from the givens already, so that's one of my A's already from the givens. All I'll need to put in is angle A is congruent to angle A, and that's by the reflexive property. And then I can say that triangle ABC is similar to triangle ADE by AA. So that was a simple proof that was to get us started. And we're going to increasingly get more difficult as we go along. Here, our goal is once again to prove the triangle similar. And quickly glancing at the question, we don't have numbers, so AA is going to be the way to go. We're told that GI is parallel to NT. And when we have parallel lines, it's usually because we have parallel lines cut by a transversal and we can get some angle relationships. And I do see a letter Z. So that tells us that we have congruent alternate interior angles. I also see the letter X. So we have congruent vertical angles. And there's our AA. Let's write this up in a proof so we can see how that would look. So our givens, we know that GI is parallel to NT. And then we said that angle IGA is congruent to angle NTA. And our reason is alternate interior angles are congruent when parallel lines are cut by a transversal, and then I can say angle IAG is congruent to angle TAN, and that is because, let me use the full reason here, intersecting lines form congruent vertical angles. And those are the two angles that we were using for AA to prove the triangle similar. So now that they're both in our proof, we can say that triangle GIA is similar to triangle TNA by AA. And we are done with our proof. Okay, in the next proof over here, we are once again proving triangle similar, but this time we have multiple triangles in the diagram. So I'm going to start off by just outlining the triangles so we can make sure that the angles that we're finding come from these triangles that we need to focus on. And already I see vertical angles, so that gives me one pair of A's already. We are told that we have a parallelogram, and in a parallelogram, opposite sides are parallel. And once again, we do have that letter Z. So we have congruent alternate interior angles. And look at that. Even though the question was a little bit different than the last one, it's the same exact information that we're using. Let's write this one out so you could see how this one will be written up. So we have parallelogram ABCD that was given to us. And then we were able to say that DA was parallel to CB because opposite sides of a parallelogram are parallel. And then from there, we can say that the alternate interior angles are congruent. Angle EDF and angle GBF. And I'm going to put that here. Alternate interior angles are congruent when parallel lines are cut by a transversal. And then we can put in our vertical angles. Angle DFE is congruent to angle GFB. And that's because intersecting lines form congruent vertical angles. And those are the two pairs of angles that we were using for AA. So now we can say that the triangles are similar due to AA. And that's the end of our proof here. Okay. Now we're getting a little bit different. If you look at the proof statement, we're proving a proportion. And we know that when triangles are similar, their corresponding sides are proportional. So we can set up a proportion involving the corresponding sides. So step 1 is we're going to prove the triangle similar. And then step 2 is we can prove the proportion involving the corresponding sides. So I always like to take a look at the proof statement, look at the segments that the proof statement is talking about and highlight them in the diagram. So that way we could see which triangles those segments are coming from in case there's multiple triangles in the diagram. So we have BC. Oh, I forget this is not the highlighter. BC. EC. So already I see this is one of the triangles we're focusing on. Then we have AB and FA. So here's our second triangle. So when we're finding angles, we want to make sure that the angles are within those two triangles. We have parallelogram ABCD, and I'm going to think about what I know about angles of a parallelogram. You might want to pause the video and think about it. But one thing I know is that opposite angles are congruent. And angle A and angle C are opposite angles of the parallelogram. And they also just happen to be in those two yellow triangles. So that gives us an angle. And then if we continue reading the givens, we have BE is perpendicular to DC. That means it forms right angles. But I only need this right angle because that's the one that's inside one of my yellow triangles. Over here, BF is perpendicular to AD. That means they form right angles where they intersect. But I only need this right angle because that's the one that's inside my yellow triangle. And now I have congruent right angles. So I have my AA. And now I'm all set to write my proof. Let's write it up so you can see what this looks like. So we have parallelogram, ABCD. We have BE is perpendicular to DC. And we have BF is perpendicular to AD. That was all given to us. And then we said angle A is congruent to angle C because opposite angles of a parallelogram are congruent. And then we had the right angles that we were using. So we have angle CEB and angle AFB are right angles. And we knew that because of the perpendicular lines, because they form right angles. And since we're using them for AA, we need congruent angle pairs. So we can say that the angles are congruent to each other. And that's because all right angles are congruent. So now we can say that triangle AFB is similar to triangle CEB by AA. And it's just one more step of our proof to prove the proportion using the sides from those similar triangles. And the way that we can justify our proportion, it's the same reason anytime you need to prove a proportion, is because we already proved the triangle similar. And we know that corresponding sides of similar triangles are proportional, and it's the same reason every single time. Now we're going to talk about proving a product. And as you can see over here, a product looks like a multiplication statement. And it's what we get from cross multiplying the proportion. But on the Regents exam, you can't write cross multiplication as your reason for the product. It doesn't get you full credit. So we just need some vocabulary. So in a proportion, there's the part of the proportion called the means and the part that's called the extremes. So when we're writing our reason, we're going to just use this fancy vocabulary, means and extremes, but all it's going to mean is cross multiplication. And I'll reference back to that when we get there. So let's take a look at this proof. And we already said that the proof statement is proving a product. So there's only 2 triangles in this diagram, but I would do the same approach as I showed you in the last one, where I would take a look at the proof statement and I would just outline the triangles that they're coming from. So the small triangle and the big triangle. And I know there's only 2 triangles here, but when you have multiple triangles in the diagram, that's really important so that you're not finding angles in the wrong triangles. So now I need to prove these triangles similar. Once I prove them similar, I can make a proportion, and then I can cross multiply the proportion to get the product that I need. In the givens, they told us that BE is parallel to CD. So I can get congruent corresponding angles. And also, the small and the big triangles share angle A. And those are my 2 A's for angle, angle. So I'm going to start writing the proof. And this proof is not a long one. It's just that our proof statement is a little bit different. So we have triangle ACD. And BE was parallel to CD. And from having the parallel lines, we were able to say that angle ABE is congruent to angle ACD. And that's because corresponding angles are congruent when parallel lines are cut by a transversal. And then we said that angle A was shared between the 2 triangles, so it's congruent to itself. And that's by the reflexive property. And from that, we can say we have angle, angle. So we have triangle ABE similar to triangle ACD by angle, angle. And from there, we need to make a proportion involving the sides of the similar triangles. So what I'm going to do is I'm just going to take the sides from the proof statement and I'm going to put them into a proportion. But then I need to double check that when I cross multiply, I get the proof statement. So when I multiply this way, I get AB times AC. Oh no, that's not what I needed. I needed AB times AD. So I have to fix that. So I'm going to put AD here. And I will swap this one out to AC. That's the one I'm missing. And now I'm going to double check. When I cross multiply this way, I get AB times AD. So far, so good. When I cross multiply this way, I get AE times AC. So it's good. Always double check that your proportion cross multiplies to give you your product. That's something that people always mess up on. And our reason for the proportion is the same reason every time. We're able to make a proportion because corresponding sides of similar triangles are proportional. And for our next step, we said that we can't just write cross multiplication, even though that's what we're doing. We have to use our fancy terminology, means and extremes. So the way we write it is in a proportion, the product of the means equals the product of the extremes. And it's the same reason anytime you're going from a proportion to a product. So in a similar triangle proof, even if you can't find the angles, you always know the ending. You're proving the triangle similar by AA. Your proportion is the same reason every time. Corresponding sides of similar triangles are proportional. And then your product is the same reason every time. In the proportion, the product of the means equals the product of the extremes. So as long as you know the ending there, you are good to go. Okay. Here's another one where we're going to be proving a product as well. If you take a look at the proof statement, we're proving a product. And this is an example where there are multiple triangles in the diagram. So I'm going to just take a look and I'm going to highlight the segments from the proof statement so I can see which triangles they're coming from. I don't want to find angles in the wrong triangles. And I see that these two triangles are the ones that the segments are coming from. So I got to find angles in those two triangles. Right away, I see that we have congruent vertical angles. And we've been seeing a lot of alternate interior angles, and I do see those here. We do have a letter Z. So I do want to say these alternate interior angles are congruent. But remember, alternate interior angles are not always congruent. They're only congruent when you have parallel lines. And if we read through the givens, they tell us that AF is congruent, AF is parallel to CT, and AF is also congruent to CT, but that doesn't give us the lines we need parallel. We need AC and FT parallel because those are the ones forming the letter Z for the alternate interior angles that we need. But luckily, since in the quadrilateral, one pair of opposite sides is congruent and parallel, it's a parallelogram. So that means these are going to be parallel as well because opposite sides of a parallelogram are parallel. And then we can say the alternate interior angles are congruent, and that gives us the AA that we need. Let's pause here and let's write this up because that was a lot. This one is going to be quite a few steps, so I'm going to need to move over to the side afterwards. So we have quadrilateral fact. We have AF was parallel to CT, and we have that AF was also congruent to CT. So that was given to us. And then we said, from that information, we could say that quadrilateral fact is a parallelogram. And the reason for that is if one pair of opposite sides are both congruent and parallel, the quadrilateral is a parallelogram. And that allowed us to say that AC is parallel to FT because opposite sides of a parallelogram are parallel. And now that we have that those sides are parallel, we can say that the alternate interior angles, angle CAT and angle RTE, are congruent. And that's because alternate interior angles are congruent when we have parallel lines cut by a transversal. And then for our second pair of angles, we were using the vertical angles, which are really nice because they're always congruent. So that's angle AEB and angle RET. And I'm going to put our reason: intersecting lines form congruent vertical angles. And then I'm going to have to continue over here with my statement reason chart. And now we're all set with our AA. So I can say triangle ABE is similar to triangle RET, and that's due to AA. And then we know we need the proportion next. So take your segments and put that from the proof statement and just put them into a proportion. And then just double check that they cross multiply to give you the product that you actually need. AB times TR, that's not what we need. We need AB times TE. So I need to modify here. And that means I'll change this one over here to TR. And let's double check. This way is AB times TE, that's good to go. And this way is AE times TR. That's good to go. So our reason for our proportion is the same reason every time. Corresponding sides of similar triangles are proportional. And then our reason for the product is the same reason every time. In a proportion, the product of the means equals the product of the extremes. And that was our last one for this video.